Hello everyone, I hope you're all doing well today. My name is Ishkhanian and I'm an honors student in the Department of Mathematics and Statistics at Concordia. In this video, I'll be talking to you about my summer CUSRA project, which was on computational thinking in mathematics. Now before we start, I would like to ask, how many of you have ever said to yourself, I hate math? Or when will I ever use this? If not all, then at least most of the students that have taken a mathematics class have found themselves to be in a position where they were struggling. The heavy emphasis on the routine algebraic computations and the lack of utilizing real-world analogies have caused the student the conceptual understanding of the material. Now, not only this, but the world around us is evolving. Nowadays, everything is done by some type of technology, which is why the students wonder why they devote hours and hours to lengthy routines and correcting computational errors when it could be avoided with a computer. Now, I am here to show you that the answer to this question is that many people don't think computationally yet. Now, our goals with this project was that we wanted to find ways of enriching the teaching and learning tools with computational thinking through the use of Mathematica software. We took all of the application problems from the course Fundamental Mathematics 1, which is offered at Concordia, and we solved them in Mathematica using the computational thinking process. Whenever possible, I also mentioned how the problems can be solved using the natural language input, which is a tool that allows you to express mathematical ideas and questions in basic English, which then the software interprets and computes it for us. I have also created several interactive videos where I explain concepts step by step and show which approach to take that will lead to the final answer. Another one of our goals was to show students how to build mathematical confidence, enjoy the process, and illustrate to them how failure and dropout rates could be avoided. This would enable many students to cross the threshold from fail to pass. Now, I keep talking about what is computational thinking, but what is computational thinking? Well, we can view it as the four-step process: define, abstract, compute, and interpret. In define, we simply define our problem. Next, in abstract, we figure out what we want to find. We say what's the appropriate formula using tools from Mathematica, and then we gather all the information given in the problem. This will help us move on to the next step, which is to compute the problem. Now, in computing, we express the abstracted material in the Mathematica language and let the computer do the mathematical computation based on few lines of code. In interpret, we finally interpret our results. It is very common for students to find the solutions but never really interpret what they found. This step is crucial to the computational thinking process because it forces us to ensure that the computer-generated result makes sense. It also creates mental bridges between the techniques we have learned and their relevance in the real world. Now I'm going to show you a few examples on Mathematica. Now we will look at a few examples on Mathematica. As you can see, I will show you how we can approach the problems using the DACI format and how we can use tools from Mathematica to assist us in solving the problem. Well, the first example here is on investments. Clearly in define, the problem is defined. It says how long will it take for $10,000 to grow to $12,000 if it's invested at 9% interest rate compounded monthly. Now, what was the first step? Well, we do abstract. In abstract, what do we want to find? Well, since they're asking us how long it will take for the $10,000 to grow to $12,000, we know that we would like to find the time t. Next, we say what is the appropriate formula here? Well, since we know that we're dealing with investments where the interest rate is being compounded monthly, we'll have to use the compounded interest formula, which is this formula here, and we define the function a of t, where a represents our future value, t is the time in years, p is the present value, and r is our interest rate. After we define our function, we gather all of the information that we have in the problem. As you can see, it says that the present value is $10,000. We know that the future value is $12,000, and we know that the interest rate is 9%. So I simply assign my variables. So I know that P will be 10,000, I know that R will be 0.09, and I know that A will be $12,000. Now, after doing all the steps, I can easily move on to the next step, which is to compute the problem. Now, what did we say we wanted to find? Well, since we wanted to find the time t, I will have to use the command solve. We use solve whenever we want to solve for any variable. So the way we can read it is solve for time when a of t, when the future value is equal to $12,000. One line of code, and we get the solution that t is around 2 years. Now, since t is in years, if you would like to get the t in months, you can multiply it by 12 and you will get the answer in months. Suppose you forgot what the formula was here. So suppose you were stuck at this step. What would you do? What can you do? Actually, a very useful tool would be the natural language input. For example, I forgot the formula for the compounded interest. Well, I can simply write formula of compounded interest, and it will show me what the formula is. As you can see here, that the future value is equal to present value times the term here. And if you compare it with the formula that we had defined above, it's the same exact. Now, here it gave us the formula, but you can also use this in order to find your solution. Well, here it says calculate present value, but we would like to find the time. So interest periods, we can put our future value to be $12,000. We know that our present value is $10,000. And we know that our interest rate is 9%. And I press compute, and you will see that n is 2 which is the same answer here. Now, lastly, the last thing we do is we interpret. As we said, it's always very good to interpret our results. We can say that we found that it will take 2 years and a month for the 10,000 to grow to 12,000 if it's investment at 9% compounded monthly. Now, another example here would be, I will be showing you a visualization. This is a material learned in this course, and at the same time, people take it in the linear algebra classes. So whenever we solve matrices, whenever we have system of equations, and we're asked to solve it using matrices. Now, if you have a 3x3 matrix, well, it's very rare for us to know that, for example, if we have an equation with 3 variables, we know that it will represent a plane. Now, a plane, think of a paper. A paper will be the plane. And if you see the shapes, they are planes here. So as you can see, we have 3 planes here. So whenever we want to solve the system of equations where we have 3 variables, well, we know that the answer will be their intersection. So it could either be an intersection at a point, or a line where they would have infinitely many solutions, or they would have no solution when they won't intersect. Now, I'll be showing you how, for example, if you change one of the variables of one of the coefficients of one of the variables, what would happen to the plane? Well, here, as you can see, as they are intersecting at a line. You can see the red line here, and here it's telling you that the solution, we have infinitely many solutions. Suppose I change one of the coefficients of the variables, you can see that it's moving. So this plane here is moving. So once it moved, it says that we have no solution. Now suppose I change another coefficient, and you can see here that we have the red dot. That would mean that we have a unique solution. And once you change, you can see that the numbers in the in the green equation, the coefficients are changing. So one of the other beneficial tools in Mathematica was to provide visualization for students. Now, we all do computations in every class, but having visualization available to us is not very common. So we try to provide visualizations in every problem that was possible. This will help reinforce the idea in our minds. So after looking at the problems on Mathematica, let's try to answer the question, what makes the use of computers essential? Well, first of all, we are saving time. If you were trying to do the same problems on paper, it would have taken you longer than a few seconds. Here with a computer, it just took a few lines of code and we were able to get the final answer quickly. My next point would be it eliminates computational errors. Of course, we are humans, so when we do it on paper, it's very common for us to make computational errors. So if we do it by a computer, we can try to avoid them. And in return, we can actually save time. For example, the problem with the matrices, this takes a long time. If, for example, if your system if you have a large system or if you have a large matrix, solving it would take a long time and you'll be very prone to making computational errors. My next point would be that it minimizes math phobia because successful and convincing solutions are assured. We also saw how easily we were able to get the solutions by using the DACI format. Lastly, it requires the students to reflect on the meaning and the value of the solved problem and of the solution. This deepens the understanding of the conceptual basis of the problems. Now, what's next? Where do we go from here? This form of teaching and learning promotes pattern recognition skills and the ability to assess the validity of the machine-computed results. This learning objective is one of the skills honed by the computational thinking and learning. And our long-term goal is to continue this work whenever the opportunity arises. A possible research experiment would be to analyze and document the impact and benefit of computational thinking on a student's success before and after enriching these courses. And here are my references. And lastly, I would like to say that I hope that once you become familiar with the concept and its potential, you'll find a way of integrating it into your own worldview. By working on this project, I have come to realize that computational thinking fits perfectly into Concordia's vision as a next-gen university. Thank you so much for listening and have a great day.